السلام عليكم ورحمة الله وبركاته. The title of the project, Synthesis and Biological Activity of Immunofunctionalized Imidazolium Salts. Introduction. Imidazolium salts are derivatives of imidazole linked by the alkylation of both nitrogen atoms in heterocycle. Imidazolium salts are a unique combination of cation and anion. Imidazolium is synthesized in two steps. First step, alkylation of the nitrogen atom yielding hydrogen in the presence of citron base. Second step, substitution R on the second nitrogen atom linked to the double bond. Imidazolium salts are widely used in versatile compounds in modern chemistry. For example, ionic liquids, precursors of heterocyclic carbene, natural products, medicinal chemistry. Shift base. Shift base are compounds that contain an imine functional group C double bond N, where R not B hydrogen according to iodic definition. The shift base moiety is formed by the condensation of carbonyl moiety of formaldehyde or ketone with a primary amine. Shift base possess many physical properties, so they have many applications, such as biological activities, heavy metal removal, catalysis, nanoparticle synthesis, polymer stabilization. Although studies linking imidazole and shift base are limited, there are some publications such as those. Aim of study: to synthesize new classes of hydrazide and immunofunctionalized imidazolium salts and explore their biological activity. Synthesis of unsubstituted benzimidazole and 2-methyl imidazole. Formation of an alkyl imidazole derivative by an SN2 mechanism. General equation. Mechanism: the reaction begins with the deprotonation of NH group in imidazole ring by NaOH. The nucleophilic nitrogen center of imidazole attacks the alkyl halide. The halide ion develops as a good living group, resulting in alkyl imidazole derivative. All compounds except the absence of NH citrate in IR. Characteristic aliphatic CH citrate indicating the presence of alkyl substitution. Synthesis of imidazolium salts, functionalized ester. The mechanism of reaction is SN2. General equation. Mechanism: the lone pair on the nitrogen atom acts as a nucleophilic center and attacks the electrophilic alpha carbon of ethyl chloroacetate, chloride being a good living group leading to the formation of a new NC bond with the chloride as a counter anion, giving the final imidazolium salt. Characterization of imidazolium salts, functionalized ester compound 7 to 12 characterized by FTIR spectrometry. A strong carbonyl citrate bond appears in all compounds, and C-bond citrate bonds confirming the presence of the ester functionality. Synthesis of imidazolium salts, functionalized hydrazide. The terminal NH2 group in hydrazine attacks the electrophilic carbonyl carbon of the ester. Subsequent elimination of the ethoxy group leads to the formation of hydrazide moiety with ethanol as the byproduct. The ester carbonyl bond in the starting compound disappears and was replaced by amide carbonyl citrate in FTIR. results and discussion of the fourth step. Synthesis of amino-functionalized imidazolium salts. The reaction occurs by condensation mechanism in which the terminal NH2 group of the hydrazide attacks the carbonyl carbon of the aldehyde, leading to the formation of an imine bond with elimination of water molecule. Proton and NMR spectra of both hydrazine imidazolium compound and the shift-based derivative from it. Both spectra display the characteristic peak of the compound's proton. In shift-based spectra, an additional peak appears for the proton attached to the carbon of the imine bond. The proton on nitrogen shifts downfield in the shift base, indicating the formation of a strong imine bond. Carbon-13 spectra of the same compound, the hydrazine imidazolium compound and the shift-base derivative from it, a new peak appears in the shift-base spectrum corresponding to the carbon of the imine group. The same process occurs in the benzimidazole compound, where the new peaks indicating the formation of the shift base become evident. The proton and NMR spectra of the two shift-base compounds, one with a methyl group and one without, show overall similar peaks. However, a clear downfield signal appears for the protons on the carbon too, while the methyl group protons give a distant upfield peak. MIC values of hydrazide and amino compounds. MIC values of all hydrazide and amino derivatives, among them compound 13 and 15 exhibit the Hyde's activity. The compound 13 and 15 showed the Hyde's biological activity with strong inhibitory effects, agents Klebsiella and Staphylococcus and concentration dependent. Cell study of hydrazide and amino-functionalized imidazolium salts. Imidazolium salts functionalized hydrazide better than amino-functionalized imidazolium salts. Imidazolium salts functionalized butyl better than imidazolium salts functionalized benzyl. Imidazolium salts better than benzimidazolium salts. Compound 13, the imidazole derivative with hydrazide and the butyl group is the most active compound. Conclusion. In this study, novel hydrazide and amino-functionalized imidazolium salts were synthesized. Structural conformational was achieved using FTIR, which showed disappearance, stretching, and clear bond, while HNMR identified characteristic hydrazide and amino compounds signals. Carbon NMR further confirmed the presence of some carbons, such as carbonyl, distinguished imidazole from benzimidazole derivatives by carbon shift. Antibacterial evaluation showed strong activity of hydrazide derivatives, especially compound 13, where amino derivatives display weaker potency but retained high inhibition at elevated concentration. Overall, imidazolium-based derivatives appear as promising antibacterial, with hydrazide requiring structural optimization and amino compounds offering better selectivity for pharmaceutical applications. Publication. Synthesis of antibacterial assessment of blue hydrazide and amino-imidazolium hybrids. Original paper, Chemical Monthly Journal. Thank you for your